Okay, today is October 24th. We are beginning the unit on chemical bonding. So go ahead. The first page on there, I included the learning targets for this unit. I've been trying to remember to do that for everyone, but every once in a while I kind of forget that. So by the end of the time that we're dealing with this, we should have went through every one of those targets. I am going to try to incorporate a lab into this unit, so the lab will probably be next week sometime. And then as we move forward, we will we will we will get more. We'll see how this relates to everything else that we've been doing. The main thing that I want you to know with this unit is the packet is going to seem really thick, but this unit moves really quickly. Um, a lot of this stuff you already know, and it's just there's a few things that I'm going to have to go back and teach a little more thorough. For example, I know I know that we're all pretty shaky when it comes to creating Lewis structures for complex molecules and things like that. So we'll have to go back and review that some. But for the most part, we are working towards finishing this within. I don't want to spend more than a week and a half on this material. So let's go ahead and get started. So starting off this chapter, I kind of gave us a couple of questions. And it really all three of these questions kind of go together. What is meant by the term chemical bond? Why do atoms bond with each other to form compounds? And how do atoms bond with each other? How do atoms bond with each other to form compounds? So let's just look at the phrase chemical bond. When we say something is a chemical bond, what's actually trying to happen here? Okay, so I'm hearing combination of electrons. It does have to do with valence electrons of why things bond, but ultimately, what are the elements trying to accomplish by bonding?
Equilibrium, something like that.
Sort of.
They're trying to acquire full valence shell.
Okay, they're trying to get a full valence shell, but ultimately what they're trying to do, and we're going to keep coming back to this statement, they're trying to get to the lowest energy state. And they're going to do this in a couple of different ways. They're either going to do this by exchanging electrons, or they're going to do this by sharing electrons equally or sharing them unequally. So ultimately, bonding is just a way that that elements reach a lower energy state. So another way that we can say this is the attraction between atoms to move to a lower G state. All right. So if we flip over to this next page, and I know this one's kind of hard to see on this screen because it's small, but so when we're looking at the interaction between any atoms, in this case we're specifically looking at an interaction between two hydrogen atoms. So what do you know about hydrogen in nature? How is hydrogen in nature always going to be found? It's going to be found?
Excuse me.
Yes.
Can you please send Mario Cerami to the attendance office?
He was heading to the band room just a minute ago, so I don't have him.
Okay, thank you.
All right, so So we know that the natural state for hydrogen is to be in a diatomic molecule. So when we're looking at two individual hydrogens that are not combined, this is not a stable position for them. It requires a lot of energy for them to be in that position, to be separated. And then as they're moving closer and closer together, the little positive sign right here is representing the nucleus. The dots are not necessarily representing electrons, but they are representing probable locations of an electron. So as the nucleus begin to move closer and closer together, they're going to a lower and lower energy state until they reach this point that they're exactly the right distance apart, that the nuclei are not repelling each other, but they're close enough. So let's say it like this. So making this statement a little more clearly. So whenever elements are bonding, like hydrogen bonding with hydrogen, the nuclei are getting close enough together so that they do not repel each other, but they still feel the attraction to the electrons of the other atom. So we're looking at this distance here, and then notice that the most dense region of possible electron activity is in between the two elements, because that's kind of that buffer that's causing that attraction. So you can underline this statement or put a star next to this statement. Optimum distance to achieve the lowest overall energy of the system. Remember, nothing happens for free. Everything has a cost. In this case, the cost is energy. Energy is going to be expelled when bonds are being formed. All right. Our energy is going to be given off when bonds are formed because, again, they're trying to move to a lower energy state. It takes energy to break bonds. When bonds are formed, its energy is given off. All right. So moving forward a little bit, again, we should know some things about ionic bonding already. And the main thing that you should know already about ionic bonding is that electrons are transferred from one atom to another. Now, so here's a question, and I do want some participation in this one. What makes an atom produce a negative ion versus a positive ion? Okay, so base it off of what we were talking about with trends last unit. What ultimately causes nonmetals to want the electrons more, to become negative ions? Okay, well, what about specifically those trends that we were talking about? What trend is that attraction for electrons? Electronegativity. The more electronegative an atom is, the more likely it is to form a negative ion. The less electronegative it is, the more likely it is to form a positive ion. So ultimately what causes something to be a positive or negative ion is that classification of electronegativity, which has to do with what Ryan was saying about ultimately the levels, because the bigger the atom, the less likely it is to want to hang on to those electrons, and the smaller the radius, the more likely it is going to hang on to it. So because of shielding and things like that. All right. So what I do want you to know, ionic bonding, or when we're talking about ionic bonding, and something that you'll see on test and higher level chemistries, is this thing of, and I'm trying to make sure I spell it right, Coulombic attraction. All right, so you will hear this phrase used, or see this phrase used, of Coulombic attraction. It has to do with Coulomb's law. And we are going to talk more about this later. But what I do want you to realize about that, they will throw this in place of saying an ionic bond. So you will see this term used instead of ionic bond in there. And I think it's kind of cheap because they're just trying to put a bigger word in there to confuse you. All this has to do with is the attraction between opposite charges. All right. Or another way that we would refer this to when we're dealing with electrons or cations and anions, ultimately this is an electrostatic charge or electrostatic attraction. So when you're describing these type of reactions, words to use in your descriptions, electrostatic or Coulombic attraction. And I'll have to check to make sure I spelled Coulombic correctly. It might be C-U-O or C-O-U. I have to look that up. And then when we get to covalent bonding, this particular textbook that I pulled this slide from, they separate covalent from polar covalent, but whenever they say just covalent, they actually mean they're actually referring to nonpolar. So a nonpolar covalent bond is when electrons are shared equally, meaning the electrons spend as much time around one atom as they do around the other atoms in the compound. And then when it comes to intermediate cases where the electrons aren't transferred or they're not shared equally, we have the third type of bond, which is just really a subtype of an overall covalent, which is unequal sharing, and it's polar covalent. And when we talk about polar covalent, we're going to look at this a charge separation in the compound itself, to where we have a partial positive charge and a partial negative charge. And we represent that by these little symbols. So a partial positive is written like this, and a partial negative is written like this. And then also, whenever we draw the compound, we're going to have this thing called a dipole moment, which is essentially an arrow that points towards the negative side. Go away. And we call this dipole. All right. I'm recording today.
All right.
So I'll post them. That's for you. That's for Mario. All right. What did you forget? Quit making fun of my son.
Super young.
He's a freshman.
I know, but like he looks younger.
He's 14. I mean, he's.
He looks younger than I was just.
All right. So electronegativity. You can read through all of this yourself if you choose to, but the big thing is electronegativity is the ability of an atom in a molecule to attract shared electrons to itself. Last year, I taught this to some of my classes. I didn't really focus on it too much this year, because it's not a concept that's really taught or really tested in AP, but this concept of END, electronegativity difference, it allows us to use the electronegativities to determine the type of bond that will form, polar covalent, ionic, or nonpolar covalent. The only problem with it is it doesn't always work, because it's easier just to look at the electronegativity chart and see how far the elements are away from each other on the periodic table, and that'll give you a better idea if it's ionic, polar covalent, or covalent. The closer they are together, the more likely they are covalent. The further they are apart, the more likely they are ionic. And then also know this last statement. The range of electronegativities values range from 4.0, which is the highest for fluorine, down to 0.7, which is cesium and francium also, if you look at the table that I gave you. So the most or the least electronegative atoms are those down in the bottom left. The most electronegative atoms are in the top right, with the exception of noble gases. But you can notice like helium does have an electronegativity that's the same as francium. I mean, not francium, but fluorine. And then as you move down, like krypton, xenon, radon, they have electronegativities as well, because they will form those bonds on their d orbitals, and they can form some funky bonds. But for the most part, noble gases don't participate in electronegativity because they already have a full octet in their valence shell. All right, so you have a periodic table with these values on there. This is that is yours. You can do with it what you want. But just depending on who published the electronegativity chart, you will have some discrepancy in the values. I'm not sure. I think this one's pretty close to the one I gave you, but it's usually like a decimal place off. I mean, it's not anything major. Again, I'm not going to ask you to calculate electronegativity difference, but I'm going to give you some values. So if electronegativity difference, END, is less than 0.4, typically it is nonpolar. Nonpolar covalent. The difference, so when you subtract two elements from each other, if you get a number, and I'll do one example, but I don't want to spend a lot of time on it. All right, if it's between 0.4, and notice that there is some overlap. If it's between 0.4 and 1.6, it's going to be polar covalent. And then if it is greater than 1.6, it'll be ionic. So for an example, if we look at carbon monoxide, CO, looking at the electronegativities of carbon has an electronegativity of 2.5 from our table, and oxygen has an electronegativity of 3.5. All right. And this is going to be one of those that kind of messes up the scale. But when we look at this, the electronegativity difference, the END, is equal to the absolute value of 2.5 minus 3.5. So the END is equal to 0.5. So based off of that, what is the most likely characteristic of this? It's going to be slightly polar. All right. So this compound would be slightly polar. All right. What about, let's use an ionic compound. So let's use like sodium chloride, NaCl. All right. What is the electronegativity of sodium? 0.9. And chlorine? Chlorine is a 3.0. Yes. 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 Absolute value. That's why I did the. Oh, 1. Sorry. I just did wrong math. Thank you. All right. So here's my boo-boo. 2.5 minus 1.5 is not 0.5. It is 1.0. That is why I'm not a math teacher. All right. So looking at the END for sodium chloride. So 0.9 minus 3.0, what do we get here? Is that 2.9? 2.1. 2.1. All right. So on this one, based off of that, what is this one going to be? Ionic, and it's going to be very ionic. All right. And then let me see one that might come out to be a completely nonpolar. So, think about those elements that form diatomics like chlorine, Cl2. On that one, we're going to have 3.0 minus 3.0. So any diatomic one is always going to equal 0. Yeah, and it's always absolute value. So it really doesn't matter which one you put first because you're going to change the sign on it. Now, again, don't focus too much on this one. I'm just trying to show you how this relates. But ultimately, what we're going to look at, so for this first one I did, carbon monoxide, what do you notice about their positions on the periodic table as far as their proximity to each other? They're pretty close. So these two are pretty close. But there is some distance. So the further we get away from each other, the more likely it is to be ionic. So like if we look at the second one we did, these are really far away from each other. And then the last one I did was chlorine combined with chlorine, and so they're close, very close together. If we did like nitrogen monoxide, NO, we have two that are right next to each other as well. So we have a 3.0 and a 3.5, which gives us a 0.5. And that, again, is going to be really close to being nonpolar as well. So this low number is going to give us, the lower the number, the more nonpolar it is. All right. So again, I am never going to ask you to calculate END. Just sometimes that's helpful if you're confused as to whether it's going to be polar or nonpolar. And END only works for when you have two elements combined. If you start putting three elements in there, then END doesn't really work in the compound. So all it can help you do is determine if an individual bond is polar or nonpolar, and which direction. You'll have an electronegativity chart, but again, think of it more in the trend. Don't worry so much about the numbers. Look at how close they are and that overall trend of high and low. That it goes, the highest electronegativities are in the top right, lowest electronegativities are in the bottom left of the periodic table. So here's some ways that you'll see the questions asked on my test and the homework on AP exam, things like that, and in future chemistry classes. If lithium and fluorine react, which has more attraction for an electron? So this is basically saying which one is more electronegative. All right, fluorine. Why?
Because it's the highest or whatever.
Okay, so we would say fluorine, and we can say because it has highest electronegativity. All right. Now, and the second question says, in a bond between fluorine and iodine, which has more attraction for an electron? Fluorine again. And it should make sense. And again, the response is the same. It's because it has a higher EN. Now, ultimately, why does fluorine have a higher electronegativity or a higher attraction for electrons than iodine? What's okay? Which one has a bigger atomic radius?
No.
Iodine. So iodine has more what than fluorine? Shielding. Iodine has more shielding, so it's preventing that nuclear charge from holding on to the electrons as tightly or attracting more. So fluorine's going to have a higher EN because it's a smaller radius and the nuclear charge extends out further. So less shielding. All right. So when we're talking about lithium and fluorine is a ionic bond. Right? So fluorine. So lithium and fluorine does this. Lithium gives its electron to fluorine, and it forms this ionic bond where you have a positive side and a negative side. Now, if we were to look at a sample of lithium fluoride, is each little individual piece of lithium fluoride going to be just one lithium, one fluorine? No. Well, think about salt. When we look at a salt crystal, is each individual piece just one sodium and one chlorine? No. It makes what's called a lattice structure. So for every little ion, we have this little thing where they bond to each other. So every lithium is going to be attracted to the surrounding fluorines, and every fluorine is going to be attracted to the surrounding lithiums, so that it kind of makes these little crystals. And we call this a lattice structure. All right. Now, and this is going to be an ionic bond. So how is the bond between fluorine and iodine different from the bond between lithium and fluorine, sorry? What class of elements are fluorine and iodine? Nonmetals. Both of these are nonmetals. So this is going to make a covalent type bond. So when we look at it, we have fluorine with its 7 electrons, and then we have iodine with its 7 electrons, and it's going to share between these two. And then fluorine is more electronegative than iodine, so that means that this side is going to have a partial negative side, and the iodine side is going to be a partial positive. The electrons are going to spend more time around the fluorine than they will around the iodine. So all right. So when I ask you to do a dipole moment and things like that, I'm just adding that in there so you get familiar with seeing it. But when we draw the dipole arrow is always drawn towards the more electronegative element. Um, when when those electronegativities are close to each other, we can a lot of times see it cancel out. But remember, these arrows, we're going to treat them like vectors in physics. They are additive. So if you have a bunch point in one direction, that's going to make a really big one. If you have equal and opposite ones, they cancel each other out. So let's go ahead and start looking at this relationship as far as ionic and covalent character. All right. So the relationship between electronegativity and bond type helps us determine the covalent character or ionic character of a compound. So I'm going to go ahead and write this in on top of this. Nonpolar covalent. So we look at this and we're looking at the electronegativity difference in the bonding atoms versus the bond type. So if you have a very low electronegativity difference, the bond type is going to be a nonpolar covalent. If it's in the middle, it's going to be a polar covalent. And if the difference is large, it's going to be ionic. So another way to look at this is increasing covalent character is going to mean that electrons are shared equally. And then increasing ionic character, electrons are more likely to be transferred. All right, does that make sense? There will be questions about ionic character, and they may give you two nonpolar compounds and they'll say which one has the highest ionic character. And what you need to look at is, all right, so if they gave you I'm just going to pretend that this is a real compound, monoxygen monofluoride versus carbon fluoride. Which one is going to have the highest ionic character? Of these two elements, which one will have the highest ionic character or most ionic character? CF. They're furthest apart on the periodic table. So now neither one is an ionic compound, but CF will have a more ionic character than OF. So again, those aren't real compounds that I know of, but it's there. I know that you can have compounds of carbon and fluorine mixtures. Sierra, you need to. All right. So it says arrange the following bonds from most to least polar. So most polar to least polar. Another way to say that, from most ionic to least ionic. Sorry. So from most polar to least polar. So from most ionic to least ionic are most covalent. All right. So again, I showed you how to do END, but I don't really want us doing that. So let's just look at the positions on the periodic table. So of these three, nitrogen and fluorine, oxygen and fluorine, and carbon and fluorine, which two are the closest to each other, or the closest together on the periodic table? All right, so this is the closest. All right. Now looking at carbon and fluorine versus nitrogen and fluorine, which one is the farthest away? Carbon and fluorine. I'll talk about that in a minute.
One step at a time.
All right, so that's the farthest, so this is in the middle. Now, the question it's asking is, which is the most polar?
So the ones that are eliminated away.
All right, so the most polar will be the one that's farthest away. So CF has greater polarity than, and then the next one's going to be the one in the middle, which will be NF, and then the last one will be OF. All right. So this is least polar. This is most polar. All right. Now, looking at this next group, and notice that we don't have all of the same element as like not all of them have the same elements in common. So we're going to have to look at some. Again, we're going to have to look at this one a little bit differently. But looking on the periodic table, let's deal with the ones that both have fluorine first. Of these two, which one is closer together? CF is closer. All right, so that means this is farther away. All right, now what's the relationship? Now CF, we have 1, 2, basically they're 3 positions apart, and then SI and F are 1, 2, 3, 4 positions apart. So SI is a little bit further away than CF. Now looking at nitrogen and oxygen, what are their positions? Right next to each other. So these two are the closest. All right. And then again, the closest together, the closer they are together, the less polar they are. And the further they are apart, the more polar. So what's the order going to be on this one? From most to least. So it'll be SIF is greater than CF is greater than NO. Do we need to do the other one? All right. So this one we should be able to get the least polar just by looking at it. Which one is the least polar? Because it's the same element, so obviously it's going to be right next to each other. It's going to have a 0 in END. And then which ones are the furthest apart? BCl. All right. So BCl is the most polar. All right. So when we write this one, it's going to be BCl is greater than SCl is greater than ClCl. All right. So again, most, least. Any questions about that? Does everybody kind of get that concept? If you ever ran into a problem where you really can't, by just looking at the periodic table and determine uh, which one's farther away from the other one, you could always go back to END and calculate that, but again, I don't expect you to do that. All right. Ionic compounds. Any compound that conducts electricity when melted will be classified as ionic. So what I want you to know about this, a solid ionic compound does not conduct electricity. Why can a melted ionic compound conduct electricity and a solid not?
Molecules aren't as close together, compacted.
What does electrons move more freely in a melted one? Electrons, and so electrons are more free to move All right. Now, I do want to point out that when I'm talking about a melted ionic compound, that's different than being in an aqueous solution or dissolved. Um, their electrons are more free to move in liquids because remember, liquids they're free to flow. They can flow from one place to another. So any compound that conducts electricity when melted will be classified as ionic. Covalent compounds really don't change a lot in their electronic structure when they're melted. And it's usually kind of hard to melt a covalent compound as well. Well, I take that back. I'm going to change that statement later. Again, ionic compounds are composed of elements with very large differences in electronegativity. And we can say this typically, and it's going into this next statement down here, a metal plus a nonmetal, or a metal plus a polyion, or you can have a polyion like ammonium plus a nonmetal. So you can have different versions of it, but it's usually made of a metal and a nonmetal or a metal and a polyatomic ion. You do have a couple of positive polyatomic ions. The one that immediately pops into my mind is ammonium, is a +1. So I guess potentially you could have a polyatomic ion plus a polyatomic ion. And then the last thing, in an ionic compound, lattice energy is energy that is released when two ions of an ionic compound come together to form a crystal. And we also call this a crystal lattice. Think of it kind of like a ladder. It makes rungs, and they're gonna attract to each other in 3 dimensions. It's 2 words. All right, ionic bonds and lattice energy. This equation is all right. This is Coulomb's law. And essentially what you need to look at is basically what I want you to see is this Q1, Q2 over R. The Q's represents the charges on the ions. So if we're dealing with an ionic compound, we're going to have one positive ion and one negative ion. Those of you that opt to take physics in the future, you're going to learn a little bit different application of this, but essentially it's going to be the same thing. In physics, you'll learn that there's really no such thing as a positive and a negative. It has to do with something else, so don't worry about that. Just worry about in chemistry, we know we have positive ions, we know we have negative ions. All right, so the charge of our first element, the charge of our second element, divided by the radius. Now, I am never going to ask you to calculate this equation. You will need to be able to know the equation. Don't worry so much about the K. This is all I really need you to know is lattice energy is 2Q over R. Q1, Q2 over R. All right. And then when it talks about the radius, kind of just think about the actual atoms. So if we have sodium and chlorine combining, so if we're looking at a reaction between sodium and chlorine, sodium chloride, we have the sodium atom, which is going to be a little bit larger than the chlorine atom. All right, so sodium is our positive ion, chlorine is our negative ion, and it's going to look like this. When I say radius, I'm talking about the distance from the nucleus to the nucleus. This is our R. So we're looking at this, and what I want you to know is the smaller Q times Q over R. The smaller the radius, the larger the lattice energy. All right, and that should make sense when we look at it. The smaller the number that we have in the denominator, the larger the lattice energy is going to be overall. So the smaller the number you're dividing by, the higher the lattice energy. And I'll make an additional statement to that in a minute. Does everybody have what they need off of that? All right. So I left this up from last year because I didn't want to rewrite all of this. So low lattice energy means a weak bond. High lattice energy is a strong bond. The higher the charge, or the higher the charge, overall charge is going to be, the higher lattice energy. The smaller the radius, the higher the lattice energy, and the larger the radius, the easier it is to break a bond. You're not gonna. It's not a comparison of how low is it. It's usually a comparison between two different compounds. So the one with the lower lattice energy is the weaker bonds. And so one compound's going to be easier to break apart than another. And that's all we're really looking at. Which one's going to be easier to break apart? No, that's lattice energy. That should have been L period E period. I have a defective brain sometimes when I'm writing fast. But again, so we're looking at two things when it comes to lattice energy. We're looking at charge and radius. and that's our comparison. So again, it should make sense that the smaller radius is going to produce a higher lattice energy, and a higher charge, a bigger number on top, will produce a higher lattice energy. So the larger the number is on top and the smaller the number is on bottom, gives you a larger lattice energy, and it produces a stronger bond. Larger the radius, the easier to break the bond. And the reason why is because it's going to produce a lower lattice energy, a smaller lattice energy, which means a weak bond. All right, does everybody have what they need? All right, moving forward. Okay, so I'm going to change this question a little bit on this. I don't want you to calculate the bond type. I don't want you to do E and D. All we're going to do is look at these as far as ionic character and covalent character. So we're going to order these from the most covalent to the most ionic. All right, so most nonpolar, molar to most ionic, which ultimately is the most polar you can get. All right, so real quick, let's just do this from what we know. Sodium chloride, is that ionic or covalent? All right, I'm going to skip the ones with hydrogen in it for now. So let's look at rubidium and oxygen. Is that ionic or covalent? Ionic. Because rubidium is obviously a metal, oxygen is obviously a nonmetal. Now, if we have a metal in the first position, like lithium hydroxide, not lithium hydroxide, lithium hydride, what is that going to tell us about the character of this one? When you have a metal in the first position, anytime you have a metal present, we're going to call it ionic. So these other two, HCl and HF, both of those are covalent. They are acids. They are somewhat polar. All right, so now let's start looking at this. So looking at the periodic table, relationship between lithium and hydrogen, how close are they?
Pretty dang close.
They're right next to each other, so these are very close. See, but we do know this is an ionic compound. Sodium and chlorine, they're very far. And then rubidium and oxygen in relation to each other, they are probably farthest apart. All right. Now, if we're ranging these, which one's going to have which one's going to be more polar in character? Hydrogen fluoride or hydrogen chloride? Why? All right, well, technically by the chart, hydrogen chloride's further apart. But when we look at the numbers for the E and D, fluorine's a 4.0, hydrogen's a 2.1, and chlorine's a 3.0, and hydrogen's 2.1. So this one's going to be more polar. I'm not sure. Okay, so then you said Yes. All right. Um, so if I had to arrange these from most covalent to most polar to most ionic, I'm going to start with HCl. Um, so I'm going from most covalent, most nonpolar, to most ionic. So this is going to be covalent. So really then the next one I would put would be the next covalent one, which is HF. Very close, very far, very close, less polar. All right, so I probably shouldn't use the greater than, less than signs here. I'm just trying to say that hydrochloride is more covalent than hydrogen fluoride. Hydrogen fluoride is more covalent than lithium hydride. Um, Sodium chloride is more covalent or more ionic than lithium hydride, and rubidium oxide is more ionic than sodium chloride. So, all right. Um, so don't overthink this question. What classes of elements typically unite to form compounds that contain ionic bonds? What classes? So like what metal and non-metal. All right. Now we're going to start looking at lattice energy a little bit. Um, sorry, not really. Just kind of explain the magnitudes. So we are looking at, guys. So we are looking at the lattice energies of salts formed with potassium. So potassium fluoride, potassium chloride, potassium bromide, and potassium iodide. Um, what? Why does potassium fluoride have a lot higher lattice energy than potassium bromide? And in this one, we're looking at the relationship between Q1, Q2 over R. Is the top number, is the Q1, Q2 going to change at all? No, because potassium's a +1 and every one of the halogens are going to be a -1, so that's not going to change. It's all going to be 1 over. So what's happening to the radius between fluorine and bromine? Which one has the larger radius? Bromine. Why does bromine have a larger radius than fluorine? It's further down the periodic table. It's further down in the group. So on this one, remember the larger radius is going to give you smaller lattice energy. So earlier I just said the statement, the reverse of that, a smaller radius gives you a higher lattice energy. So a larger radius gives you a smaller lattice energy. Does that make sense? All right. Dipole moments. All right. Dipole moment is a property of a molecule whose charge distribution can be represented by a center of positive charge and a center of negative charge. So essentially, there are poles. There are opposite poles. So to create a dipole moment, we use an arrow to represent the dipole moment. We point to the negative charge. All right, with the tail of the arrow indicating the positive charge. So again, a dipole moment is an arrow that looks like this. We're always going to show partial negative and a partial positive. I'm not so much worried about you including the number of charge or the intensity of the charge. I'm just more wanting you to show positive and negative side. And if it helps, on the arrow, the positive side is the one that's always going to have the hash mark. So this side kind of looks like a positive symbol. I shouldn't have drawn that on there. So the back side of it looks like a plus side. That's a better way to show it. All right. So let's kind of move forward with this. So there are different ways that we represent it. So all I'm really wanting to do on this is just kind of show you how the arrows go. So looking at a water molecule, all right, we have a partial positive here on this hydrogen and a partial negative on the oxygen. So which way am I going to draw the arrow? Towards the negative. So I'm going to draw it there. And then I'm going to draw it there. Now, so on this first one, this is a bond. This is a bond dipole. All right. This is just showing the dipole between two bonds, between the hydrogen and the oxygen. Now, if we consider these, guys, if we consider these to be vectors, or if we consider these two arrows to be additive, the overall dipole, and if you kind of notice it on this one, it might be hard to see on your copy, but we have this large dipole that points in general from the hydrogen side to the oxygen side. And so we have this overall positive on this side and an overall negative on this side. So the overall dipole moment is going, the hydrogen side tends to be positive, the oxygen side tends to be negative. So this is an overall dipole. And then this last one, this one shows you electron distribution, and I apologize for your copy not being in color on this one because the color is important. No, the more red it is, the more negative, the higher the concentration of electrons. All right.
The arrow shows that like the closer the oxygen gets, the more negative it gets because there's more electrons.
Yes. So let me just make the. Melissa, you had a question?
Yeah, what if there's two negative?
So when we're talking about dipoles, it's always going to be a covalent bond, so it's always two nonmetals. So essentially from our oxidation state, we are looking at two negatives. But remember, they're sharing the electrons, not transferring. So what we're looking at is where are the electrons going to spend more of their time. So the red side on this electron distribution, red tells us a more dense electron distribution. And it'll make more sense when we look down at the picture of carbon dioxide down on the next one. If you're asking what I think you're asking. All right, so the red shows more dense, the blue shows less dense. And all they did with this electron distribution is they're using the color spectrum: red, orange, yellow, blue, red, orange, yellow, green, and blue, because the blue happens to be on this side. And it really doesn't include the indigo violet. It's just these five. So red is dense electrons, and blue is, I don't even know how you would say that, low density of electrons. I guess sparse electrons. That would be a better way to say it. All right. So let's look at a different molecule than water. And, oh yeah, one other thing. So overall, is this a polar or non-polar molecule?
It is a very polar.
It is a polar covalent. All right. Now, so let's look at a non-polar molecule. Now, you can have polar bonds but still have an overall non-polar molecule. So let's treat this as two separate bonds here. So from the carbon to the oxygen on the left, which direction will I draw the arrow? Towards the negative, so toward oxygen, right? All right. Now, on the other side, we have the exact same bond going in the different direction. So from carbon to this oxygen, we're going to have another arrow doing that. Now, if we are considering these charges to be equal and opposite, and since they are the same elements involved, they're equal and opposite, what's the overall net dipole on this? The net is 0 because they cancel each other out, right? So we do not have a dipole. No overall dipole. So this is nonpolar. Yes, I am. All right. Now, when we look at this electron distribution as opposed to the one for water, what do you notice about the distribution of electrons on this one versus the other one? Okay, that's the word I was looking for, what Ryan said. It's symmetrical distribution. All right, so anytime you have symmetrical distribution of electrons, there's no dipole. And I will tell you this has a lot to do with the shape of the molecule, and it has to do with what's involved in the molecule as well. So I am going to make one more statement that I want you to have for this. I'm going to pause so that I don't. So the overall statement that I want you to get on this, guys, the overall statement I want you to get on this is that you can have individual polar bonds in a molecule, but ultimately have a non-polar molecule. Because we're looking at the net dipole on this. If we have equal and opposite charges will cancel. Yes. So real quick, we haven't done Lewis dot structures yet, but I'm just going to go ahead and give them to you. So the bond between hydrogen and iodine will look like this. All right. Now, looking at this molecule, which one's the more electronegative of the two molecules here? Iodine. So what that means is our arrow is going to go towards iodine. This is our partial negative. This is our partial positive. And that would be our dipole moment. So looking at this one, is it going to be a polar or non-polar bond? Polar. All right. Nitrogen. Nitrogen bonded nitrogen. That's actually going to be a triple bond. And then, because remember, nitrogen has 3 sites that it can bond to. And then it's also going to have electrons on the outside of this. Just looking at this molecule, if you were to look at this as electron distribution, what would you notice about the overall electron distribution? It's even, it's symmetrical. So this is nonpolar. And it has no dipole. All right. And then this last one, actually let's look at another one. Let's look at CF4 first. So looking at CF4, okay, looking at this one, CF4, what would you say the polarity of this molecule is? It's either going to be polar or nonpolar. Why nonpolar? Okay, so again, it's nonpolar, and it's due to electron symmetry. So looking at this, again, each one of these would have 6 dots around it. I was just being lazy. Because one of them is the line. So each of these lines represents 2 electrons. All right. And if we were drawing the individual dipoles, what you would see is carbon's going to represent a positive, fluorine's going to represent a negative, but ultimately these become equal and opposite and cancel each other out. All right. So we don't have an overall dipole. Now looking at this last one, carbon, carbon dichloride, and what I want you to recognize on this one is the chlorines are going to end up on one side of it, and the fluorines are going to end up on the other side of it. Now this one we do have to look at electronegativity. So when you have a structure like this one, most of the time a tetrahedral structure like this carbon tetrafluoride will be nonpolar. But when you have one that has different elements on it, we have to look at which one has the highest electronegativity. So of chlorine and fluorine, which one has the highest electronegativity? Fluorine. So our dipole is going to go like this. It's going to be greater to this side. This will be our partial negative. This will be our partial positive. And so this one is polar. All right. I will pick up and finish the next section, bond energies, tomorrow. What you can do is you can definitely do homework 6A, and you can probably do a lot of homework sheet 6B at this point, but get as far as you can. Tomorrow I'll let you finish working on those while a couple of people are working on the test.